So great. So let's get started, everyone. So we're all here. So let's look at the schedule. So let's see. So we are in week 3 of this course, and so we are finishing up the 2 parts on Bayes' rule. We'll be talking. So we work through on Thursday. So what is Bayes' rule and how do we apply this when we have data and then what we're trying to do is to so if we have data, try and figure out what is the best model that fits that data, and then through the log likelihood how we can simplify some expressions and actually calculate stuff. We will review this today, and we'll also go through the application where the prior is not uniform, and we'll so how to think about that. Like I believe I mentioned, the first 2 kind of content lectures on the probability review was going to go a little bit faster. Now that we've out of the review, we'll kind of slow down again. So I know that there was a lot of kind of manipulation of equations at the end of through the last lecture, and we'll kind of go and see this again, but in a bit more complicated form as a way of going this at a bit more gradual pace. And then the next couple lectures are going to be on convergence. If you, again, this is part of kind of the first 6 content lectures will be on stuff directed around probability, and the convergence will be about the central limit theorem, which you may have, hopefully you heard of in your probability course. We will go over the central limit theorem, but then talk about how this is used in a very concrete way within analysis of data mining and machine learning, ways where you actually have some actual content and data, and how you turn this into a bound of where you have an approximation algorithm, but you also have a randomized approximation algorithm. Okay, so maybe if you've had an algorithms course, you will have seen some of these concept of an approximation algorithm before, or a randomized algorithm. In data analysis, all the algorithms are basically approximation algorithms. You almost never get the exact thing that you want. And the data is noisy anyway, so it doesn't actually matter. You don't get the exact thing. And they're largely either randomized or they assume some randomness in the data. So we have to deal with these 2 things. And so this will give us a language of how to talk about those. So we'll spend kind of 2 lectures on how to speak that language and how to use the central limit theorem in concrete ways of how to kind of get kind of analysis of these sort of algorithms. Okay, but what is probably more interesting to you, if you see over on the your right-hand side of the screen, is on Thursday, that's in 2 days, the quiz number 1 is coming up. Okay, so you had quiz 0, so that was kind of a practice. It was a be on Canvas. It'll be about the same way. I think it's going to have it should not be, it's not supposed to be so super hard. It's if you're following along everything in class, and you don't have to get to all the details, but something you should be able to answer so pretty quickly. Again, you'll have half an hour to do it. If we will stop the lecture of the class on that day at, let's see, at 11:35, and so then the last half an hour you can do the quiz. It's a half an hour window, and during that period I will be around to answer questions you have. So I suggest you do it then. But you can, if you don't have your computer here, you need a quiet space. Then you can take it offline and so until midnight. Okay, so it should have, I think it's like the mechanics of going through and answering them you could probably do in, so 5 minutes, probably not more than 10. If you need to recall something or work something out, you know, it can take longer. Typically with these quizzes, I aim for kind of the median time to completion of a student to be about 15 minutes. Some students will take the full, so 30 minutes because they want to double check everything. And for the TAs, I aim for when the TAs do the practice of the quiz, I aim for them to be about 5 minutes, maybe, so 10 minutes at the most. Okay, so it should not necessarily be too challenging, but if you're following along, you should be able to do okay. So this is a mechanism to keep you up to date with the material in the class, so you don't kind of fall behind. You have to take the quiz to stay up to date. Okay, something else. Oh, yeah, question.
I was wondering how long are we like expected to spend on the homework, or like just general amount of time?
So the first, you know, I don't have a great amount of time, and it's not the same for all the homework, so I'll be honest about that. And it'll depend on your background. Some of you, probability is only a co-requisite for this course. So if you're taking that at the same time, the first homework might take a little bit longer. Otherwise, if you've taken it before and maybe just last spring, maybe homework 1 is going to be pretty easy. A couple of the questions are directly from a probability class you probably had before. A couple of them are going to be new questions that are about the kind of the extensions to this material, right? So the first 2 questions should be pretty, you know, hopefully not, fairly direct applications of things you've seen from probability before. The 4th question is just plotting, and it should be using kind of, you can use the collab code you did before. You just have to adjust it to this other function. Keep forcing you a chance to use that. Should not take too long, but it depends on your background in Python again. And then this question will be on, so some new material stuff we covered the last lecture and this lecture. And you know, for some people, it's going to take longer to figure this out. Some people, it's going to be quicker. This homework will be, I think, will take less time than, on average, than some of the future homeworks. Again, homework 2 will be a lot of the review of linear algebra in there. So if you're quite familiar with linear algebra, again, it should be quick. If you're not so, then it should be, you know, a bit more time. Then homeworks 3 and 4 will probably be a bit longer. They'll be all new material, okay? And those should take a bit longer time. And then I think homework 5, I think it's the end of the semester and everyone's busy with lots of projects. I think I try and make that one so it's not as time consuming again. Hopefully that answers your question, but you know, it's gonna vary a lot between students. Depends on your background and how quickly this is sinking in. Yeah. Yeah, quiz 1, and it says this on the Canvas page as well, but it's just going to be the stuff in chapter 1 of the book. So the 4 lectures that are preceding the quiz. Okay, this will generally be the case with the quizzes. It'll try and be covering roughly the 4 lectures that happened right before, not including on the day of the quiz. I will try not to include material that happens on the day of the quiz. They could be cumulative, right? There's some stuff that builds throughout the semester, and so I can always ask you a question that has to do with, say, you know, linearity of expectation at any point in the course now that we've covered it, right? So, but it's primarily supposed to be evaluating you on the prior 4 lectures, and that'll always be the case with the quizzes. That's so sometimes it doesn't quite line up and it's a little bit off, but that should, you know, I'll try and make that clear. Okay, one more thing about the quiz. There's it's basically it's open book, although I don't want you searching on like Chegg and stuff like that for the answers. I think it's stuff that either you know it and you can kind of figure it out, or you don't. Chegg is stuff like that is as likely to give you something because of some variation in notation. Might just confuse you as much. You can look in the book though, right? that's where I want you to kind of look for this sort of stuff. That'll make sure that the terminology is the same and that as the ones we use on the quiz. Though you're also encouraged to make a one-page cheat sheet where you kind of write everything that you think might be on there on one piece of paper. This will make it easier. I found in the past when we've done this in person, I used to I try to make an open book and then people would print off the entire textbook. And I'm like, okay, I don't want people printing off the entire textbook. It's a waste of paper. I guess unless you buy it from the store. But if you, but I found that, so I let them take one sheet of paper in and they found this to be a good studying device as well, helping you retain knowledge throughout the semester. So I'm going to encourage you to do that as well, even though it's open book. That way you don't have to be searching for stuff. It should be in front of you, and it's a good studying device as well. You're kind of thinking, what was the important thing from the last 4 lectures? Condensing down to one sheet of paper. The stuff you need to know for, whatever period should not be really more than that for on the quizzes, right? There's more details and stuff in the book, but the quizzes are kind of the core of the knowledge, not like the last little detail of what's going on. Yeah, question?
Is that single-sided?
So single-sided, yeah. So I will give you, to incentivize you to do this, I will give you a 5-point bonus on the quiz. Although if you get 100%, I won't give you above 100%. So not to exceed 100%, but you can get a 5-point bonus on the quiz, and you won't know your grade till after you turned it in. So if you're preparing this, I recommend preparing it on an actual piece of paper, print it out. That's usually useful, but also have it available, saved on your computer or whatever device you're taking the quiz on, I guess if your phone or whatever, so that you can easily upload it, because you'll need to upload it through Canvas. The last question will be worth, it says it's worth 0 points, but we can give you up to 5 points on that, and that just to verify you've uploaded something that's worthwhile. If it's basically you upload a blank piece of paper, we probably won't give you the full 5 points, okay? So if you make an effort, you'll get the full 5 points on this. Great, okay, so that quiz will be on Thursday. So any more questions? Let's kind of finish the material for that quiz. This will be on the Bayesian reasoning. All right. Oh, I didn't quite get all my materials out. Okay. Oh, and my charger, so I don't run out of batteries again. All right. Okie doke. All right, so we're talking about Bayes' rule. And remember, this was for events, M and D, thinking about this as the model and the, so in the data, this was written as the probability of the model given the data. So the given data we've observed, what's the probability of the model? Okay, this is equal to the probability of the data given the model. And this is something we can often calculate times the probability of the model. This is known as the prior knowledge, guess about the model, and probability of the data. Yeah.
All right, this is about the quiz, but as far as notation goes, do you have a major preference if you use PR or just capital P to represent probability? I don't know if you touched on this earlier.
Yeah, I try to use PR because I think it's a little bit less confusing. Sometimes I will accidentally forget the R, and it will be fine if you use just the P. In some cases, we'll use P for something else. I think I try and avoid this, but that's PR. It's a little bit more clear, so that's what I would prefer. But you will not get I don't think you'll get marked off if you just use a P. Yeah. But if if later on it gets confusing and you're using P for like a random variable, then you want to distinguish between these things. Okay, and in fact, okay, we'll actually see this with a lowercase p in just a second. Okay, so the first thing I want to introduce today is this notion of this symbol. This means so proportional to, okay, and so this means this is it's like an equal sign, right? But this is proportional to where I've crossed out the denominator, right? So the probability of the model given the data is proportional to the probability of the data given the model times the probability of the model. This is true if the probability of the data is fixed, right? Which is in all the situations we're going to be considering this is going to be the case. Okay, so this is proportional to, this was useful when we were trying to find a maximum probability model, right? Well, the probability of the data was the same for all the models so that we could kind of find the same maximum. So we just say it's proportional to, now I don't need to carry around this, this maximum or the models when I'm discussing this. Okay, and this is also useful. This is also important because the other change we're going to make is we're going to stop explicitly being able to write these probabilities anymore because we're going to be talking about these continuous space of models and continuous space of data as well, right? And remember then, when you're evaluating a single model, a single point, not just kind of a set of models, it's not actually a probability. We have a probability density function. And so those are, again, those are proportional to the probability in a sense. So, so what I'm going to do, right? So this proportional, yeah. So this means, yeah. Another, just to be clear, this is like saying that for probability of model giving the data is equal to C times probability of the data given the model times the probability of the model. And this is for some so possibly unknown, but fixed constant C, right? So there's something I multiplied by in front. It's possibly unknown. You know, maybe I can calculate the probability of the data, and we could have done that in the windshield example, for instance, but it's possible I can't calculate it. Okay, so that's unknown, and it's a fixed constant, so it's the same for everything, right? So this is what proportional means. Okay, and wire out of here, and so, okay, so we're going to rewrite this using kind of things instead of probability. These are going to be so PDF functions, and we're going to start by saying that. So the left-hand side here, the probability of the model given the data, this we're going to write as a lowercase p. Okay, and this will be known as the posterior. Okay, okay, and this will be proportional to, and now we're going to use F. This is a PDF. This was, sometimes we used, well, this is the F of dm. This is the likelihood. Okay, and we had written this before as, if we just want to emphasize that this is the function of the model, we sometimes write this as uppercase L of M, but we'll just write this as F, lowercase f. This is like the probability density functions, right? This is to help you remind you that when we wrote a PDF of a random variable, we always use lowercase f. We will typically be able to write this as a product of simple PDFs of random variables. So to emphasize that, we'll use a lowercase f here. Okay, and then times the last term as the probability of the model, the prior This is called the prior. Okay. So now these are all probably density functions. Okay, instead of probability. This notation, and you know, if you ever read papers, they don't state it as a probability, they state it as a probability density function. And so they'll use like lowercase letters often to denote this, right? And that's why they don't write a probability. So technically we need to use this notation to be proper because it's not actually a probability, it's a probability density. Okay, the left one's called the posterior. The first one here, the probability density function for the data given the model, the one we can calculate, is called the likelihood, and the prior knowledge about the model is the probability density function of the model called the prior. Okay. The prior, in a lot of places, the most common letter to use for the prior is actually a pi, but pi shows up in other places, so I think I've tried to use R instead here. Okay, so we'll actually be using this notation for the lecture today. So I know it's confusing because these aren't probabilities. What do P, F, and R stand for? It's kind of somewhat arbitrary, but just think of them as the probabilities, but they're over continuous functions. Okay, and again, this is proportional to. This is not exactly equal to the product of these two things. It's for the posterior is proportional to the likelihood times the prior. Okay, because there's also this PDF of the data, but that's constant everything, and we don't know how to calculate that in most cases. So we use the proportional to, and it's also proportional to a probability. There's some unknown constant, but it's actually 0, so that's a bit more complicated. But so okay, these are, you know, you can worry about the technical reason why we're doing this, but these will be quantities we can calculate, right? This is, we're doing kind of computer science, data science perspective, we can actually calculate these things. So there'll be functions we can actually calculate. Again, we talked about the maximum likelihood estimate. That was in the lecture last Thursday, where the goal was just to find the model which maximized this term, the likelihood. Okay. In the lecture today, we want to not ignore the prior, right? So we're going to be trying to maximize now the posterior instead, and that's the likelihood times the prior. This is called a map estimate, a maximum maximum a posterior, right? It's Greek or Latin or something, but so we'll be maximizing, find the model that maximizes the likelihood with the prior. That's called a map estimate, right? So we're going to be doing so the arg max is called a map estimate of this, and then the arg of the model of this is called the maximum likelihood estimate, MLE. Okay, so we talked about the MLE last time. We're going to go through that kind of a version of that analysis again, but include the prior, and we get the map estimate. Okay. Does that make sense? So good. So okay. All right. So let's go through an example. An example about the average height. Okay, and we're going to say now that we have we'll be given some data, x1 up to xn, and we'll eventually tie this back into the example from last time where we actually had this data was equal to 1, 3, 5, 9, and 12. Yeah. or at least, I mean, partially tie into this example, okay? So we can think of these as being data that we're given, and we want to estimate let's say we want to estimate the height. So we want to estimate the height of a typical student, okay? Height h of a typical student. And well, I'm going to specify this at so U of U. Okay, so we're going to do this at our university. Okay, so this might be different than the typical student across the country or across the world. Okay, and we're going to kind of assume that we're going to be given heights from average students at the university. Maybe we select some UIDs of active students, and they've reported their heights on their, and we're going to use these as the data we've sampled. Okay. Okay, and then, but what we're going to add this time is we're now going to say we now have a prior. Okay, so we have a prior over this model of the height. Okay, so and we're going to say that the this can be a function R, and it's going to be over the model of the height. Let me actually, just for consistency, say this height is m here again. Okay, so this prior to the function, and this is going to be a normal distribution of 66 inches with 6 inches of a standard deviation. Okay, so this is saying that the mean, so mu is going to be 66, and the standard deviation, sigma, is going to be 6 inches. Okay, so let's say that I gathered some data from a national database or collection analysis of students, and I said that the average student was 66 inches tall, and the standard deviation on this was 6 inches across all students. Okay, and so if I write this out, there's going to be a pi over 72, right? This is a normalizing factor. This is x, that's e to the power minus this mean, this m, our model, 66 squared divided by 2 times 6 squared. Okay, this 72 came from, again, 2 sigma squared. That was the normalizing factor in front there. Okay, all right, this is, let me see if I can clean this up a little bit. Okay, so this is a normal distribution with a mean. The mean here, 66, is the same up here, and the standard deviation shows up here and also inside that term. Okay, so this is our prior on the height of the students. Okay, this seems fairly reasonable. Okay, yep.
So I have a question. So if you want to estimate the height h of a typical student, and we're already know that the mean student is 66, why would we just say it's 66?
Okay, so this is our prior knowledge. This is like if I were to guess without collecting any data from a national database, not at the U of U. Okay, this is my guess. The mean is 66. But I think maybe at Utah, students are going to be taller. Okay, so but I want to make sure I'm not, I'm going to only get a sample. I might only get five data points. Okay, so if I only have five data points, then I might not trust those, I want to make sure those aren't outliers or something like that. And I have this prior knowledge. I think it's probably close to 66. Okay, so I want to incorporate both of these things, and we'll we'll talk about the balancing of these two aspects. But let's work through the math, and then we'll be able to see from the math how the balancing works. Yeah. So, and these are slightly different. This is, again, this is, think about a national thing, and this is like our at the U, so they're not quite the same, right? They're not, I don't completely trust the prior because of that. Okay. Okay, so we want to somehow, so combine these together, but let's say, okay, so before we actually, one of the first useful things here, before, let's say I got an estimate from the data, and I calculated that the MLE, this is from just the likelihood, likelihood on the data D, that I have that the MLE estimate, I got an answer of 5.5, right? So let's say I got an MLE estimate of, so 5.5. All right, so my prior was 66 and my MLE was 5.5. What's the first thing that I should think about? Well, I can kind of weight these two against each other and say, well, maybe if I could stick this together into this full posterior estimate, I might get a value of around 20, right? If I took a MLE of 5.5, I need to balance these two terms. I might get 20, 30, something like that. Does that seem reasonable? There's something weird going on here. These are like an order of magnitude off, right? 66 and 5.5. So it probably means that, well, this is probably in feet, and this one is going to be in inches. I may have had the wrong units. Something weird was going on here. The data did not match the prior. And in this case, well, it was off by factor 12, right? So if I multiply this by 12, I'm going to get, then I'm going to get 66 again, and these are going to match. Okay, so if the first thing to do is to kind of check that the units are right, or check that they're measuring the same thing, or something weird is going on. That's one of the first uses of the prior, to kind of check for something that's kind of outlandish in your data, or there's a mismeasurement, or you have outliers or something like that. If you just look at the mathematics, this is kind of an uninteresting thing, but in practice, when you're dealing with data, there's often noise, there's collection errors, there's translation errors. These happen all the time, and so it's worth just kind of looking at it and eyeballing what's going on, right? A famous example of this was the Discovery space shuttle. When this, I think I was a child when this went up and it exploded on launch. It was on national TV. Everyone was watching. It was very bad, and it was the reason for it. Eventually, they figured out was a mismatch in the units in some of the thing they were calculating. Okay, so this sort of thing happens. So use the prior to kind of check to make sure everything everything makes sense. So let's go and kind of calculate, how do we stick these together? How do we balance these two terms once we've kind of checked that everything makes sense? So let's write again. We're gonna go back to our, likelihood is F of the data, so given the model, and remember this is a product over all the data elements, and say G of X, and we could say this because we assumed independence here. Independence, okay. we assumed independence, so we can take the probability of each of the data points occurring and multiply these together. Okay. And so this is a product X of D, and this is, so let's say that our model, this one is going to assume that this sigma here, that the noise that we're drawing the data from when we measure someone's height, right, that there's some, this assuming that there's some Gaussian noise, and the standard deviation now is 2. So we're going to say there's a standard deviation of 2 here now. Okay. And so let's see. So this would be a normal at the centered at the data point. Okay. Now with the standard deviation of 2 and evaluated at the model. Or we can actually do this the other way around. And this is going to be symmetric, so we can actually, maybe it makes sense to evaluate at the model, and so it's centered at the model, evaluate the data. We can do that just as well. Okay, because this is gonna, when I write this out, it's gonna be the product X and D of 1 over 8 pi. Okay, because now standard deviation 2 squared times 2 times pi under the square root. Okay, exponent negative, the denominator is going to be 8 times the model minus x squared. Okay, so it didn't matter whether I centered the normal distribution at the model, that's the noise, and evaluate the data, or the other way around, because it's symmetric how it uses those terms. Okay. Okay, so this is now our likelihood. Okay. And so we can now write so let's see if we recall. Okay, so now we can write the posterior as going to be R, right? And remember, this is basically, this is P of the model given the data. Okay, and this is proportional to F D M times R, the prior on the model. Okay, and so this will again be easier to look at in the log posterior. Okay, so we can instead look at the log posterior. Okay, the log of the posterior M given the data. This is going to be, I need to be a little careful here. This is going to be proportional to the log of the likelihood. Okay, so the log, but now we can do plus the natural log of the prior. Okay, plus a constant. Okay, if you remember, there was there was also divided through by the should have been divided through by the PDF of the data. When I do a log transform, so yeah, I turn that into a sum, but it kind of, in order to do this proportional to here again, it's not quite proportional. It's not a kind of just a scalar transform. So it's not an equality. There is another term here that is the, if I have this exactly, it's going to be an equality here. I'm only going to care about the proportionality from here on down, but I'm going to have to carry an extra constant here, right? Because it's not a multiple. I'm not just multiplying by constant. I'm also I'm now adding a constant as well. Okay, so I'm going to accumulate some stuff in the constant. Again, that's not going to matter because I just want to maximize this model. And I can multiply by a constant or add by a constant. It doesn't change the maximum. But in order to use the proportionality, I need to have the constant at the end. Okay, so that's what's going on there. Oh, is there stuff in the chat I've missed? So the C is kind of a new C. It's not the same C as the constant of proportionality. Is that all the questions that were? Yeah. Okay, great. This is a new C. It's some constant. It doesn't even matter what it is. I'm just going to keep it there just to keep everything on the level. Okay, so let's try and write this out now. Okay, and so because I've done this log transform, I can kind of skip a bunch of steps here. Okay, so we're not going to go through in the full details before, but this log, this is a log of a product, and I can turn that into a sum over the data, right? And each term inside of the sum is -1/8, right? And I'm also going to push that log transform through the exponent, right? Remember, I've got this exponent after I factored out the constant in front of that exponent. That's going to go into a C. I'm going to turn that into another constant term that I don't care about. Okay, but once I've gotten rid of that constant in front, and I'm going to apply the log onto the exponent, right? And so I'm just going to have this term inside here, m minus x squared. Okay, so that's what the log, and I'm going to have a plus. Now it's going to be a C prime. It's going to be a different constant at this point, but again, a constant. And then I'm also going to have a term. Remember from our prior, we also assumed it was going to be some normal distribution. So it's going to have the same basic form here. I'm going to write minus now the denominator was, before this was 1/8, now it's 1/72. But remember, this came from this term down here, right? This is 6 squared, 36 times 2 is 72, right? So that's the 1/72 times, let's see, this is m minus 66 squared. Okay, there's only one of those guys. That wasn't a product over a bunch of terms, so I don't have to carry this sum, okay, in front there. And there was, another coefficient in front. That was a product, that constant coefficient times the exponent. Remember, there was also this this constant here in front, and that also, when I do a log transform, that's it can be plus that term, and it doesn't depend on the model or the data, so it's a constant. That also goes into C prime. Okay, so again, I've got a new constant C prime that I've carried over on the right. Okay. And now just to reorganize this a little bit, I'm going to say, again, this is proportional to minus, and I'm going to multiply through just by negative 72 here, or by 72. So this, so I'm going to pull the minuses out front. So I still have a sum over the data times 9 m minus x squared minus m minus 66 squared plus, again, there's, okay, this is a double prime because I multiplied by 72. Okay, I did that so you can kind of see the relative weights of these things against each other a bit more clearly. Okay, so now my log posterior again has this form. I need to find the model value m, which is minimizing this. Or if I multiply by -1, then I can try and maximize this. Or, oh, sorry, the model that minimizes this, but I actually want to multiply by -1, and then usually that minimizes that term. Yeah.
In the second equation, the final parenthesis after the -66, what's that one line up with? It should be included in the summation, right? The final term.
Yeah, so the sum,
That final parenthesis.
yeah, so the sum is over here.
Okay. So in the second equation,
That's not inside the sum. This is also not.
okay. So is the
Right.
final parenthesis just extra?
That's a constant, C double
On
prime.
the right of n-66 squared on the second equation.
Oh, yeah, oh, okay, great, yes. This one here,
That's- yeah.
yeah, that one shouldn't be there. Thank you. Great. Yep, I don't know where that came from. Okay, thanks. Great. So this is our expression that we need to maximize, right? Or we want to again minimize the sum of squared errors here, okay? And you know, I think you can plug in data and you can try and minimize this. Let me talk a little bit about how to interpret this before we actually do that, okay? And what this is saying is that what's interesting to look at, I think, here is this factor 9 in front here. What this is saying is that the way I've set this up and the way we've written the equation is that every data point is worth 9 times as much as our prime. Now, is this standard to do it this way? I would say no. This does not have to be the standard way of balancing that. One data point has to be 9 times more than the prior. Okay, and if I had kind of got rid of this 9, and we'll go back through and see where this 9 came from. You know, it's often common in number of situations to actually set the prior equal to as much as just one data point. This is saying I would need 9 versions, or like one data point is 9 times as important as the prior in this case. I don't really trust the prior. Okay. All right. So, but we could change this. So let's kind of do some thought experiments here. Let's look back. Where did this prior come from? Well, let me write up again the prior R of M. Remember, this was 72 pi x of negative m minus x, not x here, m minus 66 squared over 72. Okay, so this is the prior. Okay, and so what is difference between these? Why did the data point get weighted more than the prior? What's the important difference? Well, there are 2 ways. They both have the same form. They're both this normal distribution, e to the minus difference squared. Okay, what's different is the coefficient in front and the part that the distance is so divided by, right? This standard deviation. They're both controlled by the standard deviations that I inputted here. I assume I said at the beginning, and I said, assume there's a measurement error of 2 inches on the height. Maybe these are self-reported and people kind of lie a little bit. So we didn't trust it that much. So that's where this 2 came from. And the 72 came from this 6, right? It came from the 6 here about the standard deviation here. And I said, well, that's the average kind of, the average variation among people. Well, these are not quite the same things, right? I didn't quite, this is maybe not the right way to set the prior. This is, I'm trying to estimate, again, as you point out earlier, the average height, not a distribution over the heights. right? I'm trying to get the average height. So really the 66 is what's matter. And this might be a big study where they took, 100,000, college students, and then they took the average. And when you do that, and we'll see this in the next couple lectures, this standard deviation actually goes way down. You average a bunch of things together. So I actually trust this average much, should trust this one much, much more than the other one if it's an average of 100,000 students or something like that. Okay, so this 6 was probably not the right thing to use. But because I chose this at 6, this turned into a 72, which then became, the ratio between 8 and 72 is going to be, so 9, right? And that's where this comes from. Okay, so if I had instead, let's go back through and say, let's say instead of this was based on a standard deviation of 6, let's say instead I set this to a standard deviation of 0.01, right? Let's say that I have a lot of trust in the prior now, right? So now, actually, let's just say 0.1, right? So then the variance is 0.01. Okay, so now this term, the 72, turns into this guy would be, let's see, 0.02 times pi. And this is actually, the coefficient doesn't matter. That goes into the constant, so that doesn't matter. But this becomes divided by 0.02. And now I have 1/8 and 1 over 0.02. This is actually times 50, right? So now I look at if I were to get it's now the difference, the ratio between them is 8 times 50. What is this going to be like? So 400. Now it's going to be that I would take this out and I put a 400 in front here, meaning that I trust the prior 400 times as much as one data point. Right? So if I change, I said this is a very narrow distribution. It's really centered around 66 because I trust I have a lot of data that went into that, so then I'm going to weight the prior 400 times as much as one data point. So if I only have 5 data points here, it's, this term is really going to dominate, the one coming from the front. Okay, but if I gather more data points, I gathered from the whole class here. Let's say I have 100 people in the class. Well, then the data is starting to work to be the same weight as the prior. Right? It's still only 1/4 as much as the prior. I have 100 terms versus 1 weighted by 400. Okay, if next year this keeps growing, I have 1,000 people in the class, and I use all of your IDs. That's not a independent sample, but kind of where I take 1,000 samples from our university, well, then that will be worth more than the prior. And if I take 10,000 samples, right, then that'll be worth kind of the sum of those will be worth about like 50 times or 20 times more than the prior, roughly. Okay? So the more data you get, eventually it will overwhelm the prior. But if you don't have a lot of data, you trust the prior. Okay, so that's kind of how to think about what these balancing terms are doing. And how concentrated that distribution is kind of ends up determining its weight in terms of when you're averaging these two things together. Okay, that kind of makes sense how to think about these two terms. Yeah.
Why did we assume standard deviation 2?
Yeah, so that was just I just chose that. I mean, partially for this example, if I had chosen that to be smaller because I had actually measured everyone's height very carefully, then that would have been smaller, and then the weight of the data points would have been high. Yep. So, but if these are, I don't trust them very much, I weight it as a 2. It kind of goes into the modeling. There is inherently some modeling aspect into here when you're weighting against the prior. Before, when I only cared about the maximum likelihood estimate, I didn't do the prior. That didn't matter. I got the same estimate. because they're all weighted the same. But now I compare it against something else. I need to somehow do some modeling to make this decision. Yep.
So how would you explain standard deviation, like that number means, like things terms? Like, would you say this means that like it's like plus or minus 2 inches on average, or how would you like how we getting?
Yeah. So it's kind of, I mean, it depends on the distribution. It's kind of like plus or minus 2 inches, but it's determined by this normal distribution, right? So I said there's some mean M, and then there's this probability distribution, which is a normal, and basically roughly you go halfway up the height function here, and you kind of go out from the mean over, and this is the one standard deviation, the way to think about it, right? So it's technically defined in terms of the variance. It's the square root of the variance, and the variance is the average square deviation from the mean. So it's the square root of the average square distance from the true mean of it. So it's kind of a, so that's a bit more technical, but it's kind of like a plus or minus 2, but it's defined by this normal probability distribution. I could have defined a standard deviation with a different distribution over here. Said it could have been like a uniform distribution, right? It could be that the probability distribution is defined by uniform, plus or minus, well, you know, I have to make it slightly bigger than the standard deviation so that when I calculate the standard deviation through the variance, it gives me that 2. So it goes a bit past that, but then again, that's the standard deviation. So it's not exactly the range either. Yeah, but it's something kind of like that. It gives you a measure of scale of the error.
And what percent of the data would be sigma?
For a normal distribution, it's about 66%. 2 sigmas, 95%, 3 sigmas, about 99%. Yeah, so great. Okay, what should, okay, so I want to talk about a couple more things in this lecture. This was the most important part to understand. Again, reviewing this example, seeing how the prior factors in. We'll talk about 2 things more. One is I mentioned how to calculate the answer for just the likelihood, where this constant front didn't matter. But now I have 2 different ways. How do I minimize that? I want to talk about how to calculate that. It's just doing a weighted average instead of an average, but I'll just go through it in case you haven't seen before. And then talk a little bit more about Bayesian inference, which is, we're talking about the most likely models here, right? But Bayesian inference allows you to say some more powerful things about the probability distribution of the models, and what that can mean. Other uses from that if you go down kind of the Bayesian modeling part of data analysis, it's a bit harder to work with, but it gives you more powerful things you can say, and I'll give you kind of some insight into what those will be. We'll kind of do that for a bit of today, and then we won't, for mostly other than, you know, we'll touch on it the next couple lectures, but we really won't go into it the rest of this semester. There's some graduate level course offered every couple years or so that really dives into this. Okay, let's talk about, let me first just talk about the weighted average. Okay, so I'll talk about this a bit more general. I think it's a really intuitive concept, but if you haven't seen it before, it just might not click. How do you actually solve this? If I don't say, I'm sure I'm going to get questions about it. Okay, so I'm going to define this a bit more generally than what we'll need. We'll only need to weight 2 things, right? But I'm going to have I'm going to have n values. Okay, x1, x2, up to xn, and I'm also going to have n weights. W1, W2, up to Wn, and these correspond with each other, right? So I should think of them at a pair, xi and wi, and the weights will have the properties each wi will have to be greater or equal than 0. Okay, so this is going to be a common situation. I want to calculate what's called the weighted average, and this is going to be, let's call this x bar, is going to be just x, the sum over the n terms of the weight times xi divided by the sum of the weights. Okay, this is an expression that shows up lots of places, so it's good to just see it. You know, it's basically, one way to think about it is I can take these weights and I can normalize them, right? I can set, I can have an uppercase W, which is just going to be the sum of the weights. And then I can actually say, let's let PI be the weight divided by the sum. Okay, if I do this, I use PI because I can think of this as a probability. PI must now fall in between 0 and 1, right? The weight was greater than 0, so the sum of the weights must be greater than 0. So this must be greater than 0. Must be less than 1 because the sum of the, I'm dividing by the sum of the weights. Every individual weight must be smaller than the sum, okay? And if I add all those weights to all the PIs together, I'm going to have the sum of PI is exactly equal to 1, okay? So if I do this, then this term is actually also equal to PI times xi. Okay, I've factored this guy, this is uppercase W, into the weights. I've just factored it in, and now this looks exactly like an expected value, right? A probability times a value, the sum of the probabilities times the value. Okay, so the weighted average is just kind of an expected value here, which is great. Again, as I said, a lot of data analysis reduces down to kind of computing an expected value. And so if this is kind of the expected value, just turn those weights into probabilities of these xi's, right? Or if these are drawn from a distribution, but I weight them with some sort of confidence or importance, then this is just an expected value, right? And so then I'm going to claim that, you know, in order to find the point that minimizes the negative of this, once I get rid of the negative sign, then this is just an expected value. Okay, and that's the maximum a posterior estimate. Okay, so it's just going to be a weight on the xi's times 9 if I use the original weighting, and the 66 gets a weight of 1. Okay, or if I use the second weighting I talked about, where the standard deviation went down to 0.01 for the prior, well then all the data points get a weight of 1, and the prior value 66 gets a weight of 400. Okay, and that would might change the estimate based on what the data is. Okay. Okay, so this weighted average is how is the solution. I also want to kind of prove to you that the average was the solution for the sum of the squared errors. I'm not going to go through that for the case with the weighted average. It just adds to complexity. But again, let's say I have n values, x1, x2 up to xn. Okay, and I want to have a function s of x for some possible value z. Let's use m. Let's use m here. That's what we've been using. And I want to minimize, or I mean, I'd like to find right? The value m, which minimizes this expression, right? And so in order to understand this, we'll just expand it and use some calculus. And it's not too hard, but it's worth just writing this out. M squared minus 2xi m minus xi squared. And okay, and this I can write as n. If I push the sum through, n times m squared, because they're n terms, minus 2 times the sum times xi plus to n xi squared. Okay. So if this is a function, right, I've claimed this is going to be a parabola, right? As we talked about in class last time, it's the sum of these parabolas, but it's going to look like this. And I want to find the minimum of this function, and the value of m is on this x-axis here, right? So I want to find the minimum. How do I do that? I take the derivative and I set the derivative equal to 0. Okay. So if I take the derivative of this, d of delta s of m divided by d of m, right? So this is going to be 2 n m minus 2 times sum. Oh, there should have been an m here. Okay, 2 times sum times xi. Right? So this is the first derivative with respect to m. Set this equal to 0. And now I can solve for the value m. And I'm going to get that m, move one of those terms to the other side, divide by 2, divide by n. And I get 1 over m, 1 over n. Xi, right? So this is exactly the average, right? So this is how you derive that the average is what minimizes the sum of squares. Okay. You can check, I can take the second derivative of this and I can check that it's going to be positive, and that means that it's curving upwards, right? So that's actually the minimum. Okay, good. So this kind of, and if you wanted to do this with weights, and you keep track of the weights and you push the weights through here, you'll get the weighted average. But I'll leave that as an exercise. Okay, good. I think it's useful to see in case you haven't seen this before. All right, let's talk a little bit about okay, the power of this sort of so posterior here. Okay. Again, we were able to write down this posterior function, which is probability of the, or not probability, but a PDF of the model given the data, which is proportional to the probability of the model given the data, assuming that the probability exists. Okay, and so we're able to, if you remember back a couple slides, we did this log transform here. I could have basically kept track of this constant here. Some of that factored out from the coefficients in front of the exponent, and those I could have kept track of. There's a probability of the data, but actually that's not going to matter. Okay, there's a constant c here. If I want to turn it back to the probability, all I need to do is to undo this log transform, right? Undoing the log transform is taking this to the exponent, right? So I can go that this is proportional to the x of the log of p of m. So given d you know, plus minus any constant here. Okay, so the plus minus this constant, even though I didn't fully calculate this constant, it's going to get pushed back into this term, which is proportional to. So, so even though I only calculated this log thing, I can always run it back to an X map, and I can actually get the probability of this posterior, or something proportional to the probability, right, to the PDF. Okay, so I don't have the true value, right? There's this normalizing constant I have. It's not a probability, but what are things I can actually do with this? Okay, so the first thing I can definitely do is I can compare so models. Okay, so I can do, you know, I can say I've got model 1 and I've got model 2, and I want to say, well, I can say which one is more likely. I could already do that. I could say P of M1 given D is greater than P of M2 given D, and I can say that's M1 is a more likely model. But I can also, it's also perfectly fine to do M1 given D divided by the posterior of M2 given D, right? So let's say this is, say, a value 2. That means that the first model is twice as likely as the second model. There's some constant of proportionality, but when I divide, that constant factors in. So I can actually look at the ratio of these two things, and I can properly do this ratio comparison, saying this model is twice as likely as this other model. If you're doing something like hypothesis testing, sometimes it comes down to something like this, where I have, this might be some like null hypothesis, and this would be, and then this M1 might be the H1 or the alternative hypothesis. And if I find an alternative hypothesis that is something like 19 times more likely than the null hypothesis, I get like a 95% so confidence, or that the null hypothesis is not the right model. This would be how you might reject the null hypothesis, by looking at the ratio of the most likely hypothesis to some null hypothesis. Okay, so that's one of the places this comes up, and how this Bayesian view can relate to the frequentist view of things. Okay. Okay. So I can do this comparison of models, including ratios, make total sense in this case, even though I don't have the normalizing factor yet. And we also saw that this was useful, like, and with the cracked windshield example, that was the discrete setting, but that allowed me to pick out the most likely factory which improperly installed my windshield. So okay. Okay. So another thing we can do, and this is sometimes the case, is we can marginalize over some models. Okay. So remember, what was marginalization from the probability review? That's when we remove the effect of the specific choice of one of two events or random variables, right? Remember the example with the shirts, the random shirt and the random pants, and we want to find out the probability of the shirts marginalized over the choice of the pants. Well, I want to do that here with the models here. Okay, so I basically want to think of integrating over the models, over some space of models, of the probability of the model given data times some sort of function. Let's call this h of the model here. Okay, so what would this h of the model be here? This was if these models, okay, these are often going to be useful, and we'll see this a bit more throughout the semester in making a prediction. Okay, this model here, this will be making. I'm not going to use it just as a model, but I'm going to kind of say maybe I'll get part of a new data point. one of the data points I use to train, I'm going to get part of the data point. Let's say I have, for instance, I'm trying to predict the average height, and I have whether the student is a freshman, a sophomore, a junior, or a senior, and the height is different based on, you know, how far they are in the program. Maybe it's the number of credits they have so far. Maybe people tend to keep growing and they get taller the more credits they get, right? So I want to use this to make a prediction for a new student who has, you know, 65 credits at this point. Okay, so I want to then predict their height based on this, but I don't know the right model. I have the most likely model, but I have some uncertainty over the space of models. So I can try and integrate, and for every model, I'm going to make a prediction, this H function, and then I say, well, I'm going to average over them, right? I'm going to kind of average over these models. This continuous integration, again, is going to be hard, right? Because I don't know the normalizing factor here, but what I can do is a kind of a weighted average instead. I can set over some models in some set of models, and then I'm going to also calculate right. I can have a set of models I'm going to consider. Let's say the height, the mean of the model, I'm going to pick 100 possible heights, which is the average, every 1/10 of an inch for a range of 10 inches. Okay, it's not all of them, but this is kind of like a discrete integration. And then I can calculate this posterior for this, and I can divide through it, and this works as a weighted average. And so I can get it up with here. And if I make that resolution finer and finer, I assume some continuity properties, then I can get a better estimate. And this marginalizes over the choice of the model. So if the average was really higher and there was, you know, then I can factor that into the calculation. Okay, so I can do things like this. There are other ways of kind of estimating this denominator that are more complicated, but this is a pretty simple way of doing it. Okay, yeah.
And all we're doing by that, I'm just like, kind of like, well, I think it's the marginal distribution of kind of.
Yeah, exactly. The same trick that I used here to turn these weighted averages into kind of probabilities in this case. Yep. That's it. So it's exactly this trick. Yeah, and so this is, you know, I really wanted to integrate over continuous space, but I can do kind of a finite approximation. There are other potentially better ways. If the models are in some higher dimensional space, this becomes harder. And then there are these sampling regimes that, you know, you can get into the next level of courses. And then one other thing is I can think of this, I can kind of say a range of models which is most likely. I can say something like, I can kind of figure out, you know, there's some posterior distribution, right? This is M star. This is maybe arg max of M over P of M D, right? And there's some distribution over M. This is P of M D. It's going to look like some sort of it's probably going to look again like a normal distribution, and we'll talk about why on Thursday. So it's probably going to look kind of like a normal distribution. I can say, well, the model is very likely to fall in some range of models. I can again probably need to do discrete integration to get something that estimates a probability, but I can say that 95 percent of the models are going to be in this range. So I can say, well, maybe this was 66 inches, but the average is between 65 and 67 inches. I'm 95% confident of that, right? So I can try and use this posterior, that's a probability distribution, to say something even more formal about the range of these models, right? And so there's a whole field of literature that goes into doing this, not just for single point estimators, but for these more complex estimators that we'll be looking at the rest of the semester. Okay, so that we're not really going to cover in this class. You have to go to the next class, but I want to give you the insight into what this can be used for, because we're just going to be looking at the sum of the squared errors. From now on, we're pretty much going to be looking at just models that, eventually are just looking like this term here. We're going to say, I'm going to write down model. I'm going to try and minimize the sum of the squared errors, and it's going to come from all this, and there's all this other stuff under the hood, but we're going to focus on this sort of starting point for most of the rest of the semester. Okay, great. Let's stop there.